All right. So Josh just asked if we could have class outside. No, sorry. I would love to for this class. It's just a little tough to do in this size class. I actually expected fewer of you here because of the nice weather. I figured maybe you'd be like, well, I'll just watch it on video later when it's not nice weather out. But thank you for coming. I know. See ya. No. So I got off a plane from Seattle this morning at 6 a.m. My back is killing me. If I keel over, call 911. I shouldn't keel over, but ask good questions and I'll stay perky. Here's what we're going to do today. We're going to talk briefly about Boggle I'll answer any other questions about that. We're going to talk, this is the lecture, so by the way, there's 3 more lectures, right? There's today, there's Wednesday, and there's next Wednesday. And then after that, the following Monday is the final. We're doing it in class, right? So 3 more lectures, believe it or not. Today's lecture is probably the last stuff that's going to be testable. Wednesday's lecture will probably be on Comp 40. I haven't quite decided yet. I might push that to like the following Tuesday, because you know how they've given us an extra day or whatever? I haven't really decided yet. We pretty much caught up, by the way. So good job on all that. But we pretty much have caught up. And normally what I do is like a pre-Comp 40 lecture, which is basically for people thinking of going into Comp 40. Here's what you should do to prepare for it and think about over the summer and so forth. I would not require you to be, I don't really require you to be here anyway, but you are certainly welcome to stay. If you aren't taking Comp 40, we are going to talk about real stuff. It's not like it's like kind of a throwaway lecture. We are talking about real stuff, but it's not testable. So I wouldn't feel bad if you're like, I'm not taking 40 and I want an extra day off, so I'm going to go away. But that's, I would come to class and then I'll decide whether it's going to be a 40 lecture or not. Or if you want to email me the night before, if you don't want to be, come all the way down here. OK, so why is this lecture called Esoteric Data Structures? Well, so we've talked about a lot of the big ones. The data structures we've talked about are the ones that you will see for the rest of your career in computer science. You'll get asked them on interviews. You'll have to use them. You'll have to understand them. The ones today are a little bit out of the ordinary. Some of them are used very frequently, but a lot of people still don't know about them. They're the kind of ones that if you're in the interview, they probably won't ask you about these, but they might say, how would you go about doing this sort of thing? And if you pull one of these out, if you say, that's not a bad idea to use a Bloom filter, they'd go, wow, that's an impressive answer, right? So there are definitely uses for these. You will see them at various stages, but it's not like a typical data structures like lecture. So it's a little bit different. And we're going to go through 3 different things. The last one, we may not get through all of it, depending on how many questions you guys ask and how fast we go through the other stuff. But the first 2, I think, are the most interesting. OK? And we'll revisit our old friend that we love to hate, the linked list, in this one called a skip list. OK? All right, first things first. Boggle, how's it going? Going all right? OK. If I made you raise your hand, if you haven't started it, you should feel really guilty. I'm not going to. But if I said, raise your hand if you haven't started it, and you were one of the ones who raised their hand, then you should feel a little bit guilty, because it is kind of an intense project. Some people have gotten to the stage where they're all like doing above and beyond now, because it is doable. Right? It's not a project that you're like, you can't do. It's just there's a lot of pieces to it. And if you haven't figured those pieces out yet, if you haven't seen the review video, go ahead and watch that. Or come to office hours. We'll get you definitely going on your way. OK? So you got to be concentrating on that. Questions on Boggle? Yes?
In the checker program?
In the checker, the validator, yes. Yep.
That program has no idea what the valid words are. So do you have to
No, that doesn't have an idea of what the valid words are. There's different ways of attacking that. You could potentially refigure out all the valid words. Probably not going to be quite as fast if you figure out whether a particular word is valid. That's probably a slightly better way to think about it. You could do it the other way, but no, you have to redo it you have to resolve it if you wanted to go down that path. Yes. Yeah. What else? Question came up earlier. What if you had 2 words that were, somebody typed in 2 words that were the same, even if they happened different places on the board, right? Because you could have duplicate letters such that you have the same word appearing twice, and your solver needs to solve for all the combinations. So far, so good? Let's say that the person typed in top, and then pop, and then top again. How should we score that? This one should be OK, and 3 points. This one should be OK, and 3 points. This one should be no, and 0 points. You could argue it either way, but we're going to stick with the idea that this should actually come out as 3 points, OK, top, if top occurs in the board. And then 3, OK, pop, if pop occurs in the board. And then 0, no, top, even though top appears in the board. But if it's a duplicate, you should say 0 points. That's the way Boggle works. Even if it appears in the board twice, the rules of Boggle say you can only count it once. Somebody in the earlier class said, wait, that's not the way we played in our house. And I went, well, those are your house rules, right? The actual rules are you don't get to count 2 words twice, even if they're on the board twice. I think it's a little crazy too, but that's the way the rules are. We'll go with the rules. OK? All right, other questions on Boggle? Yeah?
How does the score get the output?
The score will get the output as just words. So word, word, word. No period or anything either. So you have to, I think I put in the original post about the thing how to do the CN for that. But it's just word, word, word. That's it. And then you have to decide. And it will, sorry, I lied. It will tell you OK word, OK word, OK word. Or no word. Right? That's what you'll get. You have to then score it. That's what it gets. Yeah?
Can the size of the board ever change?
You can have a board of any dimensions that are, I think we'll keep it at square.
Yeah.
But it can be any dimension. It won't change in the middle of the game, no.
Okay.
But it probably doesn't really matter.
Also, if you have 2 words, does it matter which one you count?
It won't matter which one you count. What I'm going to do is I'm probably going to sort this list, and however you return it, I'll probably sort it. I'll also probably sort your solutions. So your solutions should just have all the solutions, and once they're sorted, they'll be the same as my list, hopefully. That's the idea. What else? OK, the lack of questions tells me you guys are either really confused or really doing well. So I'm hoping it's the latter. All right? Yes? All right. I believe your code's going to be somewhat similar, because especially if you have to go through the board again for the whatever the letter, yeah, it's going to be similar. So you can recopy that. That's fine. You can reuse it. Sure. I would say I would recommend using recursion in both cases. Sure. If you figured out how to do it differently in both, that's fine too. One question that came up with was, should you check the word in the dictionary that someone gives before you check it in the board? Well, what's the asymptotic complexity of a trie? The length of the word, constant behavior, basically, right? So you get that for free. So it might not be a bad idea to check in the dictionary before you check on the board, because that's going to be a little more intense, probably. Yeah. OK. And we're going to time these. And I don't know how we're going to do the points for timing, but I will let you know, be very clear about that. It should finish for most regular boards in a reasonable amount of time. But I'll figure out the definition of that. Got one of the TAs looking into this now. Anything else? OK. All right. So the first esoteric data structure we're going to talk about is this thing called a skip list. OK? First question I have is, what are some of the problems we had with linked lists? So you guys know that I'm not a big fan of linked lists, but what are some of the issues we have with them? Alex?
Pretty much ON for everything.
Pretty much, well, not everything. Insert at the head of a list is not ON. It's constant, right?
But for a lot of the basic.
For a lot of the things, right? What are the other ones? Oh, insert at the end, sure, unless you keep a tail.
The end.
Remove from the end. What's the big one we like to do on lists? Finding things, right? Finding things is definitely ON. That's a big one, right? Linked lists are also not very good with for caching, because they're not a nice data structure in one location. But we're actually not going to solve that problem here. But so that's not so great. If we have a sorted linked list, is that going to do anything for us? Does that help us get better behavior with our find operation? I got a couple yeses, a couple no's. Let's just write a couple of these down. Let's say 3, and then 10, and then 11, and then 50, and maybe 85. Can we search through that better because it's sorted? Isabel?
I think it depends if you have an end pointer or not.
Depends if you have an end pointer. OK, I'll give you an end pointer.
Then, like, if you do sorted, you might know to start at the second half of the list. So it could speed it up, but asymptotically, it would be the same behavior.
What is that behavior? Yeah, linear. Yeah, it's linear. So,
The same, but it could speed it up.
well, yeah, I'm not sure a tail would necessarily help you too much. But yeah, I see what you mean. Having another one in there might help a little bit. Winona, you had a question or comment?
Like unlike an array where if it was sorted, you could do sort of like a logarithmic order by starting in the middle. The linked list, you can't really do that.
OK.
So even if you had one thing at the very end, what if it was like 3, 81, 82, 83, 45?
Yeah. If you had one at the end, then you'd still have to go backwards a bunch, maybe. But I like the idea of the middle. Maybe there's something to do with the middle. I'm not sure. Here's what I want you to think of. Talk to your neighbor about this. Can we speed up our search by helping the list? If there's something else we can add to this list to give it better properties. And I will tell you that it's going to be sorted. So if I give you a sorted linked list like this, is there anything we can do to maybe help it out? Talk for a couple minutes about this. See if we can do it. If you can figure something else out. Does memory matter? Not really. Not too worried about the memory footprint of this, no. All right, let's see. Hannah, what did you guys think?
We were talking about a few different things. We talked about making a doubly linked list.
OK, doubly linked list, certainly. That's a good idea.
And then also kind of using the ideas of some of the sorting algorithms, like starting in the middle and then knowing which way to go, cutting the list by half.
OK, so if you do have some middle pointer, does that help you out?
Yeah, I mean, if the thing that you're looking for is less than 11, that's only half 11.
Yeah, I think that's a good point. Yeah, I mean, now we had the comment earlier that if it could be like, it could be a weird list where everything is real close on one side and spread apart on the other. But you'll get a benefit of once out of that, right? You'll go half. You'll at least split it in half, which is kind of nice. Yeah.
I was thinking that make it doubly linked, but also have, say, a third and fourth pointer inside each node that points, say, 5 nodes ahead or 3 nodes ahead and 3 nodes behind.
OK.
That way, if it's greater than current value.
What if you made it just 2 ahead or something? That might,
If it's way bigger, go 2 over, 3 over.
OK, so yeah, but in the end, adding more pointers to this might be able to help. Yeah, I mean, you're going to add up. We're going to end up with like huge kind of things. But yeah, maybe if you do that, then you only have to go through half the list if you know, and maybe back once or something. Not too bad. Nathan?
There are lots of ways of going about this, but all you're doing is trading time complexity for having a ton of pointers.
You're trading time complexity for a ton of pointers, maybe. But we might be OK with that, as it turns out. I'm not sure. Isabel?
Well, hashing kind of ties linked lists in it. If you do like I forget which.
Hashing's going to be a little tough with this because we don't really have we don't have an array. And if we wanted an array, we'd probably just use an array.
Also could do you could break the linked list into smaller linked lists.
Break the linked list into smaller linked lists. Smaller linked lists, we're kind of doing that in the sense of giving extra pointers. So you guys are thinking of a couple things. This is the one that people have come up with, and very good on coming up with that, where you kind of think, OK, the halfway part would help, right? But what if I said halfway and then 3/4 and a quarter or something, right? Then you are trading off some more benefits of this. Or if I say skip, skip, skip. So we're kind of getting there. And I like this idea of saying, give me more locations. Because if you have to walk through the whole thing, you're going to be in trouble. So give me more pointers to the locations. All right, now, see this list here? 14, 23, 34, 42, 50, 59, 66, 72, 79. This is sorted, obviously. And this is a very interesting string of numbers. Anybody recognize that ordering? What's that? It's not Fibonacci.
The amount by which they go up decreases by 1 with each.
The amount they go up decreases, not quite. 23 to 34 to 42. 998, but then it's, okay, not quite. Think outside the box a little bit. Did anyone see that ludicrous display of baseball last night? Anybody see that? Who played last night? Anybody know? Boston and New York. New York. Any New Yorkers in here? You recognize this, Alex?
Oh, it's famous player numbers.
Not famous players. It has nothing to do with baseball, but it has to do with New York.
Street numbers?
Ah, street numbers. What were you going to say back there? It's what? It's the which train?
A train, C train.
Somebody earlier told me it was the 1, 2, 3. I would call it the 7th Ave train.
It's the one, two.
The 1, 2, 3. This is a bunch of subway stops in the New York City subway. And you can go from 14th Street to 23rd to 34th, 42nd, et cetera, right? Some miracles happen there, supposedly, right? And this is the way to do it. But if you're a New Yorker, you're not going to do that. You're not going to get on at the end there and go through all these stops. What are you going to do instead? You're going to do what? The which? Oh, the 3. What's the 3? It's the express. So here's what you're going to do. Right? There's a different set of lines. New York is an interesting subway system. Unlike the T, New York has these things called express trains, right? And the express trains, they pick the stop. I'm not sure how they exactly pick which stops the express lanes go on, but there's 4 tracks, 2 in each direction, and you can get on the express train. If you're going to go to 59th Street, you don't get on the one that goes 1423. You don't get on this one. You get on this one first at 14. And then you get off at 42nd, then switch to this one, and you go to 59th.
It's like which stops
Right.
have like the most.
It's probably, well, yeah, but in 1905 when they designed this, who knows? I mean, but yeah, it might have changed a little bit. But yeah, they've decided this for some reason, that these ones are kind of more important in the people getting on and off sort of thing. But this is an express list. Now, this almost exactly, surprisingly so, models a skip list, which is this. A skip list is a linked list that has all the numbers in it. And then it has other numbers in a different linked list that are kind of the express route. Okay? And if you want to get to 59th Street, what you have to do is you start at 14 in the linked list, and you go to 34. You get on the top one. You go to 34, then you go to 42. You can go to 72, or you can just peek ahead, and you can say, what's the next one's number? And then it's got another link that goes to the 42 below it. You go down to that link and start finding the 59. And you keep going until you've passed something. And if you pass it on the lowest list, you know it doesn't actually exist in the list. But you see how that works? It's called a skip list because you're skipping a bunch in the top and then going down. Also turns out to be pretty easy to program. Okay?
How do you determine the skip?
Well, that's a good point. How do you determine the skips? We'll get to that. Okay, we'll get to how do you determine it. By the way, did I mention that this class we're actually going to do a little calculus? This is the first class, probably the only class in the entire time that you're in computer science that will do a little bit of calculus. And it's like this much calculus. Has anybody never taken a calculus class? A couple people. No, you don't have to be ashamed of that. That's all right. A couple people have not taken. That's OK. I will show you how to do it. It is not testable and whatever. But I just want to show you that we actually can do a little bit of calculus in a computer science class, and that's why they make you take Calc 2 if you're a major for one day. I don't know. But anyway, so this is the basic idea here, okay, for a skip list. Here's how you search through it. I kind of already went through this. You start at 14, go all the way to 72, and then backtrack. These should be doubly linked, right? These are definitely going to be, in the big picture, this should be a doubly linked list. Or you should just be able to peek ahead, or you can keep a next and previous and all that. But that's how you do the searching. Okay? All right. By the way, we're calling the top list list 1. Probably should have been the other way around. We're calling the top list list 1 and the bottom list list 2. And in this case, list 2 has all of the stops or all the nodes in the linked list, and the top one has fewer. But the question that Isabel brought up earlier was, how do you actually determine what the best placement of the nodes are? Right? It's a little weird that the express goes 34 to 42 and the other one's a locals of 34 to 42. But this has to do with, I'm sure, city politics and this and that and whatever. In our list, what's the best spacing we might want for list 1 up here? Any ideas? Nobody hasn't answered in a little bit. Let's say it's long. Depends on what? Who hasn't answered in a little while? I'm seeing 10 hands that people have answered. It's kind of written up here too. How about equally spaced, right? No matter how many we have up here, let's make them equally spaced. Because in our picture, the better they are spaced out, algorithmically we're not going to like jumble anything up. It'll be the best we can do as far as going a number of steps before we have to drop down to the non-express lane or express train. Okay? So we're going to want some sort of equally spaced. We're going to have to minimize these. All right, calculus people, how do we find the minimum of something? Take the first derivative and then set it equal to 0. All right? And all the engineers are like, yes, I know this. You know? All right? So here's where I will rewrite this like this. And by the way, the searching through this is the important part. The search cost, which is what we're trying to minimize, how long does it take to search, is the search cost can be represented by the number of links in the top plus, what's that? It's not the absolute value, it's the number of. When you put the braces like that, it means the number of in this case. The number of links in the top plus the number of links in the bottom divided by the number of links in the top. Because basically, if you have them spaced out nicely, right, you're going to get to a certain one and then jump down. And before you get to the next one, you will have to go through a ratio of the top to the bottom because every so often you've got one. And the ratio of the bigger list to the smaller list gives you the extra amount that you'll have to search. In other words, you would never have to search past the next one in the previous list, because you wouldn't have stopped there if you had to do that. Okay, does that make sense? Yeah, go ahead.
Will this help us optimize how far apart we should space?
Yeah, it's exactly going to optimize how far apart we're going to space them. But first we need to figure out, like, yeah, we have to figure out based on how many are in L2, where do we put the ones in L1? And not only where, I guess it's really, we already know that we spread them equally. But the idea is, how many are we going to want is really what we want. How many do we want in this list if we have this list to make it maximal, or in this case, the minimum search amount? Question?
Do you have like more and more lists with like each being less, like more sparse?
We'll get there. We'll get there. Hold on a minute. Hold on to that thought. First, let's get through this one. Before you think about other lists, let's just think about this one first. I know, you're thinking ahead, which is awesome. But hold on this one. So let's just do this little bit of calculus. Okay, let me rewrite this little search amount like this. Let me rewrite it such that, let's say that we have L1 we'll call L1x. So we've got x plus, and then we'll call L2 n divided by x. Okay, we want to minimize that, which means we want to take the derivative with respect to x of that. Okay, and then set it equal to 0. Go ahead and do that. Take a minute. If you've never seen calculus before, go, I don't know what you're talking about. All right? I will write how I would do it on here. But go ahead and do that as well. What's that? N is the constant, yeah. X is the one that we have to minimize by. Okay? Whoops. Okay. All right. Calculus people, did I do it right? Right? Take the first derivative. Remember, even though this looks like you might have to do some logarithm or something. No, you got it backwards. Did you try to do a logarithm? You did. No logarithms here, right? Nx to the negative 1, when you take the first derivative, is negative nx to the negative 2, right? Set it equal to 0, do a little bit more algebra, and you end up finding out that the optimal number of links in the upper list is the square root of the number of links you have in the bottom list. OK, that turns out to be the minimum, and we've shown that here. I suppose it could have been a maximum. We could have taken the second derivative and blah, blah, blah. But let's not worry about that. Too much calculus for computer science, I suppose. OK, so we minimize the amount. We end up with the number of links in the upper list being the square root of the number of links in the other bottom list. And by the way, you're going to have to round. I mean, things aren't probably the odds are probably slim that you would necessarily get the exactly square root. But you might. 25 in the bottom, 5 in the top. Right? And we already said we wanted them equally spaced. So it kind of looks like this. You have the square root of n links between them. And you have n of those square root of links, right? So now what is the search time? It's the square root of n plus n divided by the square root of n, right? If you do a little algebra on that, you'll find that we get 2 times the square root of n. OK, relatively simple algebra there, too. OK, common denominator, et cetera. What's that?
How much faster is that asymptotically?
Well, asymptotically, it's better than n, because square root of n is better than n. So it's like square root of n better, right? Yeah, this is more or less the asymptotic behavior, because you're the worst case, right? You might have to go through square root of n of them, but you only have to do that, you might have to go all the way through the square root of n of these, and then only a couple more here, right? Only the square root of n more there. So square root of n plus the square root of n, 2 square root of n. Not there. Yeah, no.
Does this make insertion more expensive because you're readjusting the spacing?
Well, we haven't gotten to the spacing yet. We're saying if we already know what elements are in here. OK, we haven't talked about how we're going to get there. In fact, that brings up a good point. Later in the class, we are going to use this quarter to actually do something to help out when we actually want to build this. OK, we'll see. It gets kind of interesting, I think. OK, but everybody kind of, at this point, hopefully you saw the calculus. It didn't blow your mind. And you kind of get that if we do this, we have beaten our time to search by a factor of 2 square root of n, right? Because instead of being n, it's now 2 square root of n, and that's better. OK? Now, we had the question earlier. What happens if you have multiple lists? Why not make this one also have its own list above it? Right? Why not? If you had a billion here, and this is like a square root of a billion, why not make it a square root of a square root of a billion up to here? OK? If we add a third list, OK, what's our search going to be? If it's not 2 square root of n, what would it be with a third list? Any guesses? 2 cube root of n? OK, 2 what? 4th root of n? I don't know. 3 what? 3 cube root of n. Oh, I like that one. If you add a third one, you can do the math if you want to. But 3 would give you 3 and then the cube root of n, right? If you had k lists, you would get kth root of n, right? It goes up like that, right? 4 would be 4 fourth root of n. 5 would be 5 fifth root of n, right? And I know you're going, oh my gosh, what's a fifth root again? I forgot, right? But if you have k lists, it's kth root of n. If you have log number of lists, isn't it just log n, which is the equivalent of the k, times the log nth root of n? OK? The log nth root of n is what? Mathematically speaking, if we take the log nth root of n, and we want to figure out what that actually equals, it's actually kind of cool. If you set this equal to x, we can figure out what that equals, right? If we raise both of these to the log nth root, or log n, That will get rid of the log nth root here, right? So we say if we raise this one to the log of n, and we raise this one to the log of n, we get n equals x to the log of n. And if I say it's log base 2 of n, what number to the log base 2 of n gives you n? 2. 2 to the log base 2 of n gets rid of the log base 2. So turns out that the log of nth root of n is just 2. Meaning that we now have the total, if we have log n lists, we now have 2 log n behavior, which is logarithmic searching, right? So we just have to create more lists until we get that. Question: where else have we seen a log n list of levels? Binary trees, right? Right? If there's 64 elements in your binary tree, you will have log base 2, which is 6 levels. OK? This is now kind of mimicking the behavior of a binary search tree, which is kind of cool. In fact, it looks like that when we draw it out. Yeah?
But then why not just use a tree instead? Why go through all the effort with all the pointers?
Yeah, it's a good question. Why not just use a tree? First of all, this is pretty darn easy to build, right? It's just a bunch of linked lists. And you can build linked lists until the cows come home, right? They're not that hard to build linked lists. If you've got one linked list class, you can augment it by saying some nodes have the ability to point to another linked list instead of just their next, right? You could say they're below or something, right? That's the only difference. So it's pretty easy to build this. That's one general solution. OK? Yeah, or reason.
Linked lists all using the same data, or do they have separate lists? Like the 66 in list 1 and list 2, is that the same physical 66 in memory, or are there two, or is it copied?
It's probably copied. These are 2 separate linked lists, so it's probably copied. So it is more space. You could probably be clever about figuring out the pointers to make them the same data. Yeah, you probably could. Yeah, Isabel?
How would you optimize, or how would you determine like the optimal number of lists you would want?
Well, we actually said optimally we would like log n lists because we're going to get log n behavior. So log n lists.
That will determine how many extra lists.
Yeah, that will determine how many extra lists. If you already know how many things you're going to put in this to begin with. OK? So that was the first answer to why this is like easier than binary trees. If I draw it like this, doesn't this kind of look a little like a binary tree? Like it kind of spreads out a little. It's a little weird with the 14 and the 79 and the first one up there. But in general, this looks a little bit like a binary search tree, right? In kind of the visual aspect of it, right? And the other nice thing about this is that, well, as I said, it's nice and easy to build these because they're linked lists. That's not going to take too long to do, right? And in addition to that, there's no need to balance these, right? Remember, that was the other ugly part to a binary search tree was unless you did some sort of AVL operations on it, it wasn't going to be balanced necessarily. This kind of ends up balanced. If you already have all the elements, you can very easily stick them into this and make sure that it's balanced in the big picture, right? So there's no need to do extra balancing. So this is why it's not a bad idea. Well, we'll get there when we got to talk about how to actually build it. Yeah.
I was going to ask something similar. Just wouldn't you if you added any of these, would you have to change the entire dynamic?
Well, yeah. If you're going to add to this, you're going to have to change the dynamic. So let's figure out how to build this, right? I mean, Janelle said this, and Isabel, you've all kind of said, hey, there's a problem with this. Building it, you don't necessarily know how many stops you're going to have to be, and how many things you're going to have to begin with, right? Until you finish the bottom row. Right, which means you know all of them, right? So here's this is a very, very cool way of building this, OK? We know we want log base 2 n lists, OK? Log base 2 is either 1s or 0s, right? What do coins give us? Heads or tails. Isn't that kind of a 1 or a 0 sort of behavior? Okay, so what we can do, we could try to keep all these perfectly aligned, right? We could rechange them and recalculate, but that's kind of like keeping a binary search tree balanced. It's not easy to do, right? We could try to do that. If we knew them beforehand, we could certainly do it, right? But you're not going to get it perfect unless you know all the ones, or unless you want to take way too much time to do it. Okay, you're not going to get it perfect. Here's the cool part. And this is, by the way, the first use of probability that we will have in a data structure. The next thing we do is the second use, or the second thing. But we're just going to flip a coin. Anybody good at flipping a coin? Well, can you flip it and catch it? In a previous class, somebody kept having to drop it on the floor. Anybody think they can flip it and catch it? No? He's like, no? You think you got it? All right, I'm going to throw this back to you. All right, let's see if I can get it back there. Oh, no, I goofed. See if you can find it. Is it under the chair? Pass it back. I should have had it pass it back. I said, no, well, we're going to, yeah, no, whatever.
No, it hit something.
You got it? All right, try to get it back to Tammy back there. All right, yeah, pass it back. Should have passed it. I forgot about the ceiling. Forget about the ceiling. So we're going to flip the coin. You got it? You got it, Tammy? OK, hold on. Don't flip it yet. OK, we're going to flip a coin. Here's the strategy. This is really clever. Here's what you do. If you're going to insert a number into the list, all the numbers have to go on the bottom level. We already kind of said that, right? That's the local one. It stops everywhere on the subway. OK, so all of them are going to go into the bottom list. All right, and you search to find that point. And by the way, you start searching from the top left, and you go top left down. So we always have to have some top left. OK? After you insert into the bottom, you flip the coin. OK? And that coin flip determines whether or not that element gets promoted to the next higher list. And don't we want half the elements in each list to be promoted to the next list? And if we flip a coin, aren't on average half the numbers going to get promoted? Well, not square root. That was for only two lists. We want log lists. We want half in each one. OK? All right. And then if it comes up heads, you promote it to the next one. And then you flip again. And if it comes up heads, you promote it to the next one. If it comes up heads, you promote it to the next one. OK? And if it comes up tails, you stop and get another number. OK? We're going to try this. All right? Here's what I'm going to do. Every level must have it's kind of a sentinel node, which tells you where the leftmost part is. I'm just going to call it negative infinity. It can be negative, like whatever min int is or whatever. But we're going to do that. Every list will have a negative infinity in it. OK? All right. Somebody give me a number. 5. OK. We're going to make a doubly linked list here. And I'm going to add 5 in here. Tammy, are you ready?
Yeah.
Flip. All right. What is it? Tails. We're done. Good. OK? Somebody give me another number. 72. I'll put it way out here. All right. 72 for now. This is the bottom list. I'm just putting it here because we get other numbers. OK, flip. Heads. So now we have to promote it, right? So what that means is we're going to have a second list, negative infinity here. And we're going to go over here, and we're going to get another 72 like that. And this is going to be like that, and we're good to go. OK, somebody give me another number. Oh, no, sorry. Flip again. Tails. We're done. OK, somebody give me another number. 14. OK, 14 is going to happen somewhere in here. So how are we going to find it, by the way? Right? We're going to find it by checking 72, saying, no, that's too far. So we're going to go down here. We're going to check here. We're going to 5. And then we're going to go to 72 too far. So it's going to go in the middle here. So I'll put it somewhere in here. What did you say? 14? 14. OK, 14 goes in there like that. OK, flip. Heads. OK, this one gets promoted up. So now we have 14 here. And like that, flip again. Heads again. This one gets promoted up. 14 here. And now we're going to have a sentinel one here, kind of the top left, so we know where to start, right? Like that. OK, flip again. Heads. All right. 14, negative infinity, Like that. OK, flip again. Tails. Whew. I ran out of board space. OK, let's do one more number. Somebody give me one other number.
42.
42. OK, so 42, how are we going to find it? We're going to start up here, go to 14, right? And there's nowhere else to go, so we got to go down, down. We go to 72. It's too much, so we go down here. 72 is too much, so we know that it's got to be in here somewhere. 42, doubly linked list there. Flip. Heads. Gets promoted up. 42. OK, flip. Tails. And we're done. Now, do you get the idea that this is going to, in the end, on average, half of them are going to go up to the next level. And on average, half of these are going to go up to the next level. And on average, half of these are going to go up to the next level ad infinitum, right? It's going to keep going like that until your list is completely built. Yeah?
The problem with that is if the list isn't quite big enough, you won't get close enough to 50/50.
If the list isn't big, right, if the list isn't big enough, we're talking asymptotically here. We're going to be able to build a big list, right? Let's say we put 1 million elements in it.
So, but like that means you have to have like a guarantee in there that the list is at a certain.
Yeah, that's true for everything, though. I mean, if you,
The top two lists are the same.
the top two lists are the same. But if you added 100 more elements, I bet the top two lists wouldn't be the same. On average, the top list would have 2 elements. The next list would have 4. The next list would have 8. The next list would have 16, all the way to the bottom, right? On average, that's the way it would work out, which is logarithmic behavior in terms of the searching. OK, so that's a good way of picking it. Thanks for the flipping. Good job. You can keep the quarter. Yeah.
Just out of curiosity, wouldn't this take up, like, especially when you're talking about a huge number of elements, like 1 million elements,
Yeah.
this would not only be non-cache friendly, but just take up a huge amount of space.
Yeah, it does take up a fair amount of space, especially if you're not clever about using the same link there.
So in terms
Yeah.
of what, in real life application, what exactly would this be good for?
Well, it's easy to build. I mean, let's put it that way, right? You don't have to balance it, right? It is fast. It's logarithmic behavior, which is what we want. You know, you're not going to get logarithmic behavior out of with a dynamic array. You will if you keep it sorted, but keeping a dynamic array sorted, remember, is difficult because you have to move a bunch of elements. There's no moving of any of these elements, right? But when we're building this, we're not moving anything, right? And by the way, deleting from this, if we wanted to delete 14, just delete all the 14s, right? You know, I'll go to all lists. It's a logarithmic thing there, and delete all the 14s. And that's pretty easy, right? So no moving of things there. So it's not bad in that sense. Cecilia.
When you added 42, you went from negative infinity and then 14 and then down, and then you went over to 72 on the second level.
Yeah.
Wouldn't that be a waste if you were going to add it at the bottom anyway? Can you do that?
We don't know we're going to add it at the bottom yet. You have to figure out where to add it. It might have been farther down the line, right? You basically, and you can peek ahead, by the way. You don't have to actually go there. You can peek ahead and see what the next one is. You can do that. But you're right. I mean, to search for 42, we start up here and we go to 14, and there's nowhere else to go, so we have to go down. Nowhere else to go, so we have to go down. 14, you peek at this one, and you say, oh, it's 42. That's where we are. So it's not hard to find in this case, right? If we wanted to find, well, actually, most of these are pretty easy to find in this one, right, in this list. But you may have to kind of zigzag down, but it's still a logarithmic traversal.
But wouldn't you want to go down to the bottom anyway if you're going to insert?
You do have to go down to the bottom anyway, but you need to find it first. And you don't want to find it by going straight to the bottom and linearly searching. We want a logarithmic search to begin with, right? So you want to do that logarithmic search down to find where you need to put it in. Yeah, good. Other questions on this? All right, not a bad data structure. I mean, again, not one you'll see that often. And really, it's probably not better than a lot of other ones you might pick. But you could implement this. Maybe I'll make you implement one on the test. No, I'm kidding. I wouldn't do that. But if I gave you another project, you could probably implement a skip list pretty quickly, right? It's not that hard to do. Inserting it's not hard. You need to know probability, but that's about it. Question? Yeah. Say. Well, yeah, any kind of time you need to have a searchable list, you could use this. I mean, are there other better solutions most of the time? Probably. If you already have a binary search tree built, not, you know, and it's balanced, probably not going to see this that often. But like I said, it's a unique one, and it shows you that there are, like the probabilistic insertion into it's really clever. So, you know, seeing that you can think outside the box in some of these things and get interesting behavior is kind of cool. All right, anything else? Yeah.
Is this fair game for the final?
It's fair game for the final. I won't ask you to code it, but I mean, I could ask you about how to link. I could ask you how to insert into a linked list, or into a skip list, and why it ends up being probabilistically,
More
or
just like talking about it.
more or less, yeah. Kayla.
So if we're using the express train example,
Mhm.
we're inserting into, like if we wanted to get to 59th Street, as you said,
Yeah.
we're on the express train. How do we insert to 59 if we're the closest to 40 seconds?
If we're on the express train, let me go back here. Let's say that we ended up with this one. Where is it? This one, right? And you want to insert which one?
Go to 59.
Oh, we want to go to 59. OK, so we search over. We start going this way. We get to here, and we search one more. We might peek at this one and say, do we want to go to 72? Or you look at the little sign, and it says, hey, 72 is next. Ooh, I better get off. This is how you do it in real life, right? You get off here, and you go to the next one, the next express lane, or next express one. In our case, we have lots of express trains.
So you just have multiple lists. So you just go
Multiple lists, and you just go between the, you go down, always go down. You don't go back up a list. That's it. Josh?
So essentially, the
Okay.
line one is a linked list,
They're both linked
which
lists.
the elements are additional linked lists.
Yeah, maybe. It's a linked list that each node has an additional pointer that could point to a list below it.
But it's still like a side pointer and a down pointer.
Yeah, a side pointer and a down pointer, a next and a down or something. Yeah. Winona?
In terms of the probability, would you use a program to sort of be like, oh, heads or tails?
Yeah.
Like if
You use a heads or tails program. Just a binary, a pseudo-random number generator would work just fine. Yeah. Dan, do you have a question?
So you could actually improve this based on the data set that you're given using various probability statistics.
Yeah, if you knew the original list, you'd want to spread this out perfectly.
Well, yeah.
And or if you knew what kinds of things you were going to search for, but
Like the way that New York City does it, I'm
yeah.
assuming it's based on traffic patterns.
Yeah, sure.
So like,
Mhm.
let's say you had a little traffic counter on each thing and had like a rating from like 1 to 10.
Yeah.
You go down and see like, get all the 10s, the 9s, and the 8s, and like what stops there.
Yeah, exactly. Like if you're a city planner, you might want to think about exactly that. You'll go, hey, look, 42nd Street, that's where a bunch of Broadway shows are or something. And so you can, most people are going to get off there, Times Square, So yeah,
So if you have a known data set, you could use skip lists in the same sort of manner.
yeah, if you have a known data set and you know how it's going to be accessed, sure. Yeah, you absolutely could. Yeah, absolutely could. Yeah.
Would there ever be any application for like a diagonal pointer or something to like
Yeah, I was thinking that.
right and down?
Right, instead of going straight down, you might want to go there. That's not a bad idea. Yeah, although this may not exist. So that's the only problem, is that might be the last one in it, But not a bad idea. And then you'd kind of go, if this one doesn't exist, you need one to get to this one, So you probably can be tricky about it and start doing it. What?
It's doubly linked anyway.
Well, it's probably doubly linked, but null doesn't point backwards, right? Yeah. Anything else on skip lists? Interesting data structure. This is an esoteric one. You're not going to see it every day. OK, so let's see. We've got to deleting, as I said, you just delete everybody straight down. Easy to do. OK? Let's talk about another data structure. So clear your minds of skip lists for a minute. Now let's talk about another data structure. This is another one that you will not see that often, although I've seen it more and more in the last, say, 5 or 10 years. More people are finding some cool uses for this. And I'll let you think about it, and then I'll give you one that's kind of neat, too. This is a probabilistic data structure in a completely different sense than flipping a coin. But this one blows your mind a little bit when you think about how it's used. A Bloom filter is efficient, space efficient. Okay, what it is it's going to be a set, okay, which is elements in it that aren't duplicated, but elements in it comprise a set. And you can ask that set, do you contain the following element? Okay? It happens to be probabilistic in the sense that if you ask if it contains an element, it might not give you the right answer. OK? And you say, well, what use is that? We'll get there. OK? Bloom filters definitely tell you whether an element is not in the list. But they can only tell you whether an element is possibly in the list. OK? So here's how it works. If I say to this Bloom filter, do you contain 7? And it says, nope, no 7. That's guaranteed that 7 is not in the set. I never put a 7 in, and that's fine. But if I say, Do you have 8? It'll go, maybe, right? And that maybe is a probabilistic determination. Okay? It might be in the list, it might not. Probably is, but you don't know, depending on what the size of the list and everything. Yeah?
But if it can definitely tell you that someone's not there, then it could possibly mean it must be there, so otherwise it's saying it's not there. Like, why?
No, it could possibly be there, but we don't know. It might not be there.
So, but if it's not there, if it can definitely tell you that it's not there,
Yeah.
then if it's not there, then it is there.
Nope, not true. If I say, do you contain 7, and you say, no, 7 is not in there, we know that's true. But if I say, do you contain 7, and you say, maybe, you can't ask it again and get a no, right? You can only get a maybe if it's possibly in there. You don't get both sides of it. Does that answer your question too, or is it still a little hazy?
Like how, like why would it be a maybe?
Oh, you'll see. Trust me, you'll see why it will be a maybe. And once you see it, you'll go, oh, okay, I get it. I bet you will. Yeah.
Are there multiple sets, or is this just like one data set?
One set. In fact, it's a really small, like it's a very efficient set. Like it's a very small amount of data. Like you would love using this one if you had little memory in your computer because it's great. But it's not. It doesn't give you the answer you might want, right? If you need to determine whether a number's in there, you can't use this. If you have to determine whether it's there. I will give you a good example in a little bit. But let's talk about what it does first. And this will answer your question about how it actually works. We call these things false positives and false negatives. Have anybody taken a psychology class where we talked about false positives and false negatives? Here's the way it works in this one, right? False positives are possible. It'll say, yeah, maybe it's in the list. And that's a false positive. It says it's in the list. You say, well, it could not be in the list, and that was the wrong answer, right? But a false negative will not occur. It will not occur. So it can't say, nope, 8's not in the list, when in fact it is in the list. Okay? So that's the difference between the false positives and false negatives. All right. How do these things work? And what's efficient about them? Well, we use this thing called a bit array. A bit array, much like the coin flip, is a bunch of 1s and 0s. Okay? You've got an array, and it's 1s and 0s in there. Now, normally, if you're doing this efficiently, you won't have a whole int dedicated to a 1. You'll have you probably won't even have a bool, which under the covers is really an int. You'll have an int where you cram all the bits in there, and you do some fancy math elements to tell whether that bit is in there or not. When you get to comp 40, if you take that, you will learn all about compressing numbers into these kind of bit arrays. But as far as we're concerned, you can compress these up to like 32 times for a 32-bit integer, because instead of having 32 different integers, you can compress them all into one 32-bit integer where each bit is represented as this array. We're not going to worry about those details, but just know that it can be really well compressed.
It's like a long number.
It's just going to be a number, and you can take and all numbers, remember, a byte is 8 bits, right? That means each one of those, like an 8-bit number has 8 different positions. You can have a 1 or a 0. Okay? So that's the way you think about it. Again, we're not going to go into the details of this. Feel free to look that up. But this is what it looks like. Just an array. Okay? Again, compressed or not, but this is how we can represent it. It's just an array of 1s and 0s. Here's how this thing works. Okay? You start out with an empty list. Okay? And you have these hash functions. So this is a hashing function data structure. But you use them in an interesting way. I have 2 hash functions here. You've seen these before. 13 minus x mod 13 mod 7. And then 3 plus 7x mod 7. Now, as it turns out, I've screwed up on this. Anybody know what this will always give me? 3, yeah. Screwed up on this one. This is a terrible hash function. It'll always give us 3. It works fine for this example, but because it just always ends up modding by 7 and you add 3, so you multiply by 7, and so it always becomes 3. So somebody brought that up in the earlier class, and I hadn't noticed it before. But anyway, different hash functions. The number of hash functions is important if you want a better data structure. We're just going to use 2 in here. You could use 3 or 4 or 10 or whatever, but the number of hash functions you use is going to give you a better probability of being correct or not. Okay? All right, so we've got these hash functions. And what you do is you pick a number. and you hash it using both those functions, and that will give you a number, right? We said this one always gives you 3. So we're always going to go to 3 here. And if it's a 0, you make it a 1. And if it's a 1, you leave it a 1. Okay? The only time you change these is from a 0 to a 1. Okay? Hopefully your hash functions are independent and not silly, like they always produce the same number. But what you're going to do is you're going to apply this, and there's a huge Wikipedia article on it, which is great. You're going to apply this. You hash all those values, and then just set the various bits to a 1 if the hash value gets to that bucket. So here's the example. Okay? We're going to look at 129. 129 for hash function 1 gives you a 1. For hash function 2, it gives you a 3. Of course it does, right? So it gives you a 3. But what you do is you go to place 1 in the array, and you say, that's a 1. And you go to place 3, and you say, that's a 1. Okay? You just set them like this. All right? So far, so good. Okay, let's take a different one. If we have 483, well, 483 in the first hash function gives you a 4. Second hash function gives you a 3. Right? But you set those 2 bits. You set the 4-bit as a 1, and the 3-bit already was a 1, so you don't change it. You just leave it a 1. At this point in the table, 3 of those bits are 1s. Here's where it gets cool. How do you find out if 129 is in the table? Do the exact same thing. You hash the first one, and you find out that it's a 1 and a 3. If they're both 1s, you can say, yeah, I think 129 is in the table. Yeah?
Basically, if there's a collision,
Ignore
and because you
the
ignore,
collisions.
that
Yep.
makes it sometimes to be possible.
Yeah. Well, let's look at, we'll see how a false positive actually happens. Okay? Check 129. That's how you do it. And you say, look, it's probably in the table. All right? And you say probably because you can't do any better than that. Here's why you can't do any better than that. Let's say that you check if 123 is in the table. 123 for the first hash function gives you a 0. 123 for the second hash function gives you a 3. And you look and you go, OK, the first bit is, or the 0th bit is a 0. If it had ever been put in there, wouldn't that be a 1? By definition of the way we put it in there. So if you find a 0, you know that it's not in there. Does that answer your question about why it's not in there now? How could I have this one also be a 1? Some other hash function or some other number happened to make this bit 1. And some other hash function happened to make this bit 1. So if you check there, and the next example will show you that, right? If we check 100, well, 100 maps to 4 and 3. And guess what? 4 and 3 are, that shouldn't be highlighted over there, but 4 and 3 are both 1s. So you have to say probably in the table, but you're wrong. Right? It's a false positive. Okay, and why is it a false positive? Because the numbers do collide in the hash table, and you just don't worry about it. Okay? Let me show you an example online. Okay? This example is for, there's a 15-bit array here. Okay, and we're going to enter some strings. Let me make it a little bit bigger. Okay? All right, give me some strings to enter. Last time they made me do, last year when I did this, somebody said Chris, and then somebody else said Greg, and then somebody else said is. And then everybody was raising their hand in a second after that. But I think it was like a banana or something. But anyway, something like that. So give me something. Doesn't have to be me. Chocolate. Chocolate, like that. OK, so we're going to add that to the Bloom field. Well, watch what happens. Chocolate, there's 2 hash functions, FNV and murmur. They map to a bit 11 and bit 13. And you just mark those. And in this case, they're green. They're 1s now. OK? All right, somebody else give me another one. Mocha. OK, Mocha maps to 7 and 13. 7 and 13. So we do have an overlap already. All right, what else?
Frogs.
What is it? Frogs. Still food, I suppose. OK, that maps to 4 and 8. Yep, so there we go. One more? Murmur, of course. Murmur, not a food that I know of. Murmur like that. OK, so there's another one, and that maps to a couple there. Now, we've got all these in here, and there's a lot of bits in this one already set, right? And the more bits you have set, the more likely you're going to get a hit. Down here, it actually tells you based on the fact that there are 15 bits, and based on the fact there's 2 hash functions, and based on the fact that we've added 4 things in there, 22% probability of a false positive. Okay? So let's see if some things are in there. Okay? Let's test if chocolate's in there. Chocolate says maybe. Maybe it's in there. Right? Tells you maybe right here. Right? Maybe it's in there. Okay. Let's look for something else. Let's look for potato. I heard potato. Okay, potato may be in there. Why is potato in there? 8 and 8. Well, 8 and 8, they're both the same, so it happens to map. There's only one chance. So yeah, potatoes may be in there, but we didn't put it in there. So it's a false positive. How about something else? Ostrich. Still food. 8 and 9, maybe. So yeah, there you go. So we're not doing so well here. Yeah. All right. We haven't found one that's definitely not yet. Well, we did that one, I think. Tufts. Tufts is definitely not in there. Why is definitely not in there? Because 3 and 6, 3 is a 0 right now, and 6 is also a 0, so it's definitely not in there. We couldn't have put it in there. Now watch. If we put Tufts in there, watch what happens. 3 and 6 will become done, and now it's in there. You see how that works? And guess what? Because we put another thing in there, our probability now went up to 36% of a false positive. Yeah? Yeah, it's a good question. It depends on how many items you think you're going to put into it, and it depends on it depends on how big your bit array is. Yeah. So there's there's various, and we're going to do a little math on that in a minute. Yeah.
I was going to ask about the bit array and how large you want to make it.
Yeah, it depends. You can play around with the numbers if you want to see, but it should be relatively big. I mean, you probably a 15-bit one is just too small. Make it at least 32 because that's an integer, right? Probably want to make it 64 at least, or even bigger, depending on how much stuff's in your data structure, or how many things you're going to put in there.
Why do you want something that only gives you like a maybe?
That's a good question. Okay. Well, since you've been thinking about it for a few minutes, can you think of any time where a maybe's an all right answer, but a no is a good answer? Like, can you think about things like that? Talk to your neighbor about this for a few minutes. I want to see if you guys come up with some. And then I'll give you an example that's used. Okay?
Is he the father?
You know what? That's not a terrible one. Let's say a test where it's a swab, right? And if it's no, then that's awesome. If you know it's not, then you better do the one where you have to take blood. It's a good example.
False negative for like something bad. Aside from that, like if it was negative and you were positive.
Yep. Well, a lot of these like tests for diseases are that way, right? I mean, let's say you wanted to test to see if someone had a bad disease. Saying yes is going to make them go a little nuts if you know. But if you say no, and they're like, okay. But if you say yes, well, then you have to do another test. What's that? Yeah, I think in that case, you might want it the other way around. You wouldn't want to say no and have them have the disease.
Yeah, no, that's what I was saying.
Oh yeah, okay, yeah.
Or it's kind of like the way it's kind of like maybe is like the whole like just thing. No is like
Yeah, I guess you're right, Josh. Can't flip it around. Not this data structure, no. Yeah.
A good one would be like if a person lives in a town, because people live in different towns, they might be there currently or they might not be.
But if they're not, does it matter?
They could be traveling.
I know, but why is it better to have a? What does it matter if th're not? Is that better? Like, I'll give you some more examples too. But okay, all right. Let's see. What have you guys thought of? Okay, we had one good example. Caleb, what do you guys have?
test for diseases and pregnancy.
So test for pregnancy, right? If you get a no, you're like, that's okay, right? If you get and if it was a false positive, that would be bad, right? No, I'm going to go out partying, right? No, you don't want that, right? But if you say yes, then maybe okay, I better do another test because it might be or might not, right? Go to the doctor and actually have them draw blood and make a test for real, right? So that's not a bad example. Anybody come up with some other ones, or it's not a bad? Janelle, do you have it? How would a spam filter do it? They do use them for spam filters.
Comment spam, where if the higher proportion of comments you get are spam.
Yeah, you would only if you know it's not spam, then you can send it to your inbox. If you know it is, or if you think it's spam,
Put it in a queue or
put it in a queue to review or something like that. Sure. Yeah. Yeah. Nathan?
You could reverse it with something like Google's promotions filter. So if it is definitely promotions, you put them in that. If you're not sure, you just put them in the main inbox.
If you're definitely promotions for the Google, for the filter in the, oh yeah, for the Gmail filters. Like, yeah, if you want to put them into various boxes. Gmail, well, I should say Chrome, made by Google, does use it. This is the example that, that I use for, to show you this. Chrome uses it in a very interesting way. Have you ever gone to a website, and instead of the website coming up, it's this big red screen with this big angry message from Google that says, don't go there, this is, there's viruses on that page, or there may be viruses on that page or something, right? Well, what they've done is they've applied a Bloom filter, okay? And if you go to a web page, and this is on your local computer, they don't want to have to ask their big server like every time you go to a web page, right? They just have on your computer, they just have a little list, and it's a Bloom filter of all the different sites that they know that have viruses, right? And if it comes up that it's not a virus, they send you to the page because it's definitely not in their list. And if it's not on their list, it's not on their list. If it comes up as this might be in the list, then they go check the big server where they have the actual list, right? So they use that for making this determination, and then they don't have to check the giant list on your computer. Yeah?
another Google one is for search indexing. Have I gone to this page before?
Have I gone to this page before? Yeah. They probably do that. Yeah. Yeah. If you've not been to the page, it'll be a different color.
So they can go faster for indexing the entire internet because people get
Oh yeah. So they can. Oh, if they've gone to the page or not. Yeah.
for their own search
Right.
index.
Right. If it's maybe, then they'll probably skip it or whatever. Yeah. Interesting. Okay. So that's how these things work. Okay. Let's do a little quick math on how you figure this out. This is not testable, but it just shows you that there's a little bit of math that shows you how they got that probability before. Okay? All right, little probability here. Let's say that you have m number of bits in your bit array. Okay? The probability that a bit is not set to 1, okay, is 1 minus 1 over the number of bits. Okay? In other words, if you 1 over the number of bits will give you the probability that it's a 0. If you do 1 minus that, that'll give you the probability it's a 1. Okay? If you apply k hash functions to that bit, okay, then if you raise the 1 minus 1 over m to the k, will give you the probability that the bit is not set to 1 by any of the hash functions. One of the hash functions would be 1 minus 1 over m. Any of the hash functions you have to multiply by the number, or you have to raise to the number of hash functions that you're using. Okay. All right. So that's including the actual number of hash functions. If we're going to insert n elements, well, you need to multiply the number of hash functions by the number of things you're inserting. So that's going to just raise your same total to the number of elements times the number of hash functions you're using. Okay, so then you've got the probability that a certain bit is still 0 after n insertions. To get the probability that a bit is 1, because that was 0, we're going to do another one of these fancy like subtract 1, because probabilities are between 0 and 1. So if you subtract 1 from it, it gives you the opposite. So in this case, it's going to be the probability that a bit is 1 is just 1 minus that answer. And we're getting there, right? 1 minus, well, the answer on the previous page raised to the number of hash functions is testing the membership. Because remember how you test membership. You say apply the number of the hash functions to the new number and check whether it's all those ones are 1. To get that probability, you raise the thing on the previous page to the number of hash functions again. And interestingly, this is approximately equal to 1 minus e to the negative kn divided by m raised to the k. If you apply either one of these, you will get the probability of a false positive. Okay, so for the one we used with the example of two things being inserted, like 129 and 453 or whatever it was, the probability for an 8-bit array with 2 elements and 2 hash functions, assuming they're independent hash functions, is about 17% false positive. Okay? And if you go back to the example we had before, where, whoops, if you go back to the example we had before, if we keep adding stuff, right, stuff, keep adding that, you'll notice it keeps going up. We're all of a sudden to 44%, right? More stuff, right, will be now up still 44 because I think we just added the same. We added the same twice, right? Jelly bean, right? OK, and then 54. So we're getting up there, and our bit array is getting really full, right? Because there's only a few places where you can't find a position that's empty. OK. Expanding it is a little tricky. In fact, it's really tricky. Expanding it's almost impossible. You'd have to go back to the original data set. OK. There's another. Yeah, go ahead.
If you fill up the entire bit array, would it be 100% false positive?
Yeah, it would be 100% probability of a false positive, right? Well, some actual positives would still be in there. So you have to do the calculation, but it wouldn't be, you would never get a no, but you might get, everything else would be either true or a false positive. Yeah.
So when would you expand the data? Would you ever?
Well, you couldn't really expand it. You'd have to re-enter all the original data, right? The other problem with bit arrays is there's no way to delete from a bit array. Because if you try to delete, then you end up, let's say you delete some number, well, maybe it'll make some other number appear as a false negative. Because now there's zeros in there that shouldn't be in there. So you can't delete from this at all. OK? There's no way to do that. You could keep a second Bloom filter that has the deletions, but then you'd get false positives in that one. You certainly could keep a list, an actual list of deletions. But you're going to have to do a little bit more work to figure it out. So that's definitely a downside to this. Downside to this. OK? Yeah?
So like, what if Google figures that one URL doesn't exist anymore or no longer is malicious? Do they create a whole other filter?
Yeah, they probably have to create a whole other Bloom filter. Yeah. And I've actually seen this in practice before, where I've seen web pages that were not viruses or got cleaned and took a while to propagate through the filter process, right? They had to they had to propagate it through a little more difficult. Now again, in that case, it might come up as probably being in there, but the real list would not have it in there too. So you could always take it out of the real list if you keep that separately from it. Yeah. OK. So that's Bloom filters. Running time. Turns out running time is pretty good. All you have to do to figure out if something's in a Bloom filter, hash a bunch of functions and check the bits. Constant runtime, right? It's basically on the order of the number of hash functions, which is kind of nice. And because they're independent hash functions, if you have a parallel processor, you can run these hash functions on different processors and get the results back really fast. You don't have to do them one after the other. So it's pretty efficient, really efficient, very fast. Okay, efficient and fast is exactly what we like. OK, the last one that I don't have time to cover is this thing called a rope, which is kind of basically how you do strings if you don't want to have linear behavior. It's kind of neat. You can look at the notes on that, but we won't go over it. And it won't be on the test, obviously. Questions on Bloom filters or skip lists or Boggle or anything else?